start the stream. All right, I'm going to try to talk. I'll apologize for annoying you with my sniffling and coughing, but I'm trying. Just don't come within like 5 feet of me, and you should be okay. So what did we do last time? Do you remember? It remembers. It wants me to jump back into where I left off. Interactions?
Yeah. Interactions among continuous predictors.
Yay! Good work on the reading there. So what do interactions do? What is their role? When would you introduce one into a model, and what does it do? What do you think?
So they can make the main effect more positive, less positive, more negative.
They can make main effects more positive, more negative, or less negative. So if it's less something, then you're talking about a diminishing effect. You're weakening the effect of the predictor. If it's a more negative or more positive, then you're enhancing it. What kinds of research hypotheses do interactions answer? Research questions, I should say. There's a key word that starts with an M. I'll play hangman. M-O. There it is. Moderation. Yeah. The idea that the effect of one predictor is not uniform across the sample. It's that it interacts or depends on the level of other variables. So does this matter? It depends. That's the question of moderation. Moderation and mediation, by the way, not synonyms. Do not get those mixed up. So we're focusing on moderation in cross-sectional models in anticipation of being able to do the same thing in longitudinal models with more than one pile of variance. So we did two-way interactions, and everybody did pretty well with that, I think. Do you want to try three-way interactions? Why not, right? Because we will see quite quickly that three-way interactions show up in longitudinal models in terms of either how time-invariant predictors moderate quadratic change, or you can have a two-way interaction affecting the slope for time. So three-way interactions are more common than you would think. So I'm picking up on slide 15 here. Can you hear me okay? This is, okay, good. This is about as loud as I can do, I'm sorry. So last time we looked at examples of how we understand a two-way interaction by focusing on what it does to the main effects. The same logic can be used to understand what three-way interactions do, just at one order of complexity higher. So if you have a three-way interaction, you would say that the main effects, the three variables that are interacting, each of those you would refer to as a conditional main effect or a simple main effect. It's the idea that it is specifically the effect of that predictor when the two interacting predictors are held to zero. Whatever zero is defined by your centering. We then talk about what the two-way interactions do to the main effect. So if you have a three-way interaction, that implies there are three distinct two-way interactions. Each of those makes its constituent main effects more positive, less positive, more negative, less negative. And then the new part, the three-way. The three-way interaction takes each of the two-way interactions and makes them more positive, more negative, less negative as a function of the third variable. So you have a lot of different choices for how you walk your way through these coefficients, and which way is most helpful is usually determined by your research questions and the design. I'll show you some examples of those in just a minute, but here's a chance for us to practice a little bit. So we'll do some in-class practice here. So let's say that I have an intercept that's 5. I have three predictors, x, z, and w. I have the simple main effect of x is 1, simple main effect of z is 0.5, simple main effect of w is 0.2. So if I could tell you that the model has an x by z interaction of 0.1, what that means is that that two-way interaction is conditional on the third variable being 0. So it is specific to the zero value of the W third variable. So how would I talk about that? So let's fill in the sentences here. For every 1 unit change, that's a delta sign for change in x, what does this interaction do? So we're looking at x by z interaction. For every 1 unit change in x, what happens? Help me fill this in. I'll get you started. The effect of z becomes so this is what we did last time. This is just review. So x is the moderator, z is the slope of interest in this sentence. Okay, let's back up. Here's my effect of z. Okay, that's my main effect. So I would say that y goes up by 0.5 for every unit increase in z, dot, dot, dot. What's the end of the sentence? When, if z interacts with x and w. So this is y goes up by 0.5 for every 1 unit difference in z when
W and x are 0?
yes, so this is a specific simple main effect. If I have a two-way interaction between x and z of 0.1, then what does that interaction say happens to this main effect of z as a function of x? As x increases by 1 unit,
That becomes 0.1 higher.
the effect of z becomes, I'm going to go with more positive, by 0.10. All of these numbers are positive, so this whole page is a more positive. I'm just trying to get you used to putting the coefficients in sentences. If I go the other way, the effect of x is 1, so y goes up by 1 for every 1 unit change in x when or your turn, when what is true?
Effect of x becomes thinking of positive.
Yeah, so you you didn't answer the question that I just asked, but you did answer the one that I was going for here. So that's fine. So we start with an effect of x. The effect of x is 1 if z is 0 and w is 0. This interaction right here, x by z, says that that effect of x becomes more positive by 0.10 for every 1 unit change in z. Next, let's go the other way. X by w, small interaction, 0.01. If we talk about w as the slope for w is 0.2 when x is 0 and z is 0. For every 1 unit change in x, what happens to the effect of w according to this new interaction? Your turn.
The effect of W becomes more positive by 0.01.
There you go. Becomes more positive by 0.01. And I'm just going to copy paste here. What do I need to change?
X.
Yep, now it's x. And if we go down here, now we're talking about the z by w interaction. So for every 1 unit change in z, the effect of w becomes more positive by this new coefficient. And if I need this one, I just need to change it to the other one. So you can see the pattern. The two-way interaction takes the slope of one of its variables and makes it moderated by the other variable. So to talk about an interaction, you can't talk about change in y. You have to talk about change in slope. The interaction takes the simple effect of one of the variables and makes it more positive, less negative, less negative as a function of the other. Now the new part, three-way interaction. Same logic. The role of the three-way interaction is to take each of the two ways and moderate them as a function of the third variable. So, same pattern, one level of order higher. For every 1 unit change in x, what happens? You want to do it?
Would that be the interaction of z and w?
Yep.
Becomes more positive by 0.00.
Mm-hmm. Yep, that's it. You got it. And what goes here? Let's see. Right side of the room, or my right, your left. Stage left. Yeah, sure.
XW.
Yep, XW. And last one. Tian Pong, you're up.
Since the interaction of X.
There you go. That's it. And if we had a four-way interaction, it would take each of the three ways and make them more positive, less positive, more negative. So once you see this, you can't unsee it. It's like one of those magic eye puzzles, which coincidentally I have never been able to see, even though I use that as an analogy. The hard part comes in translating this into English. All right?
Okay. How do we interpret these now?
Okay, so let me give you a chance to practice. We'll do that in just a minute. So the model gives you three main effects, three two-way interactions, and the three-way. That's the list of coefficients you get. But because of that three-way interaction, it predicts an infinite number of other main effects and two-way interactions that are conditional on alternative values besides 0. So I want you to know how to ask for those according to what the model says. And so this is, you'll get a chance to practice this in your next quiz, but we can practice it here. So given this model, this again is just a simple regression model, but the same logic is going to apply for longitudinal models as well. Simple effect of x. How does this model tell me for any level of W and Z what the effect of x is going to be? Do you remember the rules? First step, find all of the terms that have something to do with x. So, do I need beta 0? No. Hey, welcome. Do I need beta 1?
Yes.
Yeah, I'm going to cheat here. Beta 1 plus. Can I just do B? I'm going to run out of room otherwise. Thanks. Do I need beta 2Z? Nope. Beta 3W? Nope. Do I need beta 4?
Yes.
All right. So beta 4, because this is the slope for x, I don't need the x anymore, but I do need the w. Here, I'll put the time sign in there. Like that. Do I need beta 5? Beta 5 times what? Z. I got to keep the z. How about beta 6? Don't need it. Nothing to do with x in there. Do I need beta 7? Yes, I do. But I gotta take the x out. There. So this then says the effect of x is given by this linear combination.
I was just saying it changes the different level of the different levels of W and Z.
Exactly. So the coefficient for beta 1 that the model is going to give you is for when W and Z are 0. And you can see why that is, because that's the only point at which all of these terms drop out and you're left with just beta 1. But you can figure out what the effect of x could be for any other value besides 0 using this equation. And this is the basis for writing estimate statements. They're called estimate statements in SAS. They are model constraints statements in M+. They are lincoms in Stata. They are test statements in SPSS. What did we call them in R? I forget.
For
These thingies.
these just be the coax or the code?
No, it's like it's an extra package thing. We looked this up. What's it called?
Oh, it wasn't the estimate.
Yeah, it's the analog to estimate in R. Do you know what this a linear hypothesis test or something like that?
I have to look it up.
Yeah, you go look in your email. I've answered this question before, and I can never remember what it is. But point being, every program has a way to do this, to ask for linear combinations of the fixed effects, so that you can ask for these sorts of predictions. Robert sent around an announcement for a workshop on mediation and moderation to the EMS students, and this is exactly the kind of stuff that they would teach you, except they probably give you a macro to do it. This is called decomposing interactions or probing interactions. That's what this is. I hate the word probe. It makes me think of South Park. Any South Park fans here? No?
I've seen South Park.
South Park, yeah. The very first episode, Cartman talked about having anal probes, and that's always what I think of when I hear probing interactions. So it's not a nice picture. So let's practice this one again. How do I get the model to tell me what the slope for z should be for any combination of its other variables? What starts it off? Let's go through my list. Do I need beta 0? No. No. I need a beta 2. Because at a minimum, that's what the slope for z is. What else do I need? Beta 5 times x. Beta 6w. Beta 7 xw. Yeah, there we go. Last one, W. What starts it off? Beta 3. Beta 4 X. Beta 6 Z. That right? Beta 7 X and Z. There. So when we write these estimate statements, what goes in there is the reference to the predictor that it's the beta 4. So in SAS, for instance, rather than writing beta 1, you would write x. And the next term that you would write would be x by w. And the next term would be x by z, and then x by z by w. But the values that you're plugging in next to those words, they come from the values of the moderator variables. So if I wanted, here, let me make another line down here. I'll show you what this would look like. So if I'm writing an estimate statement, it would look like this. x1, and then this would be x by w, and then I would fill in whatever value of w I want it for. So let's say if I want the predicted effect of x for somebody with a w of 4. Okay? The next one would be x by z, and I'd have to say, how about this? Somebody with a z of 2. Sure. Then the next one would be x by z. Sorry, I'm being inconsistent in my capitalization. That's how you know I'm sick. That's going to bother me. Now, what goes here? 8. So if we do this on the second line, and we'll get a chance to practice this for the example for today as well. This one starts off with z. Then we have x by z. If, let's say, we want an x of 3. And then this one is x or z by w. And what did I say I wanted for w? I wanted 4. And then x by z by w. Now what do I put? So this is the tricky part. Same term, different number. The first time through, x is the slope that we're trying to estimate, and so the values you plug in are specific for z and w. The next time through, now z is what we're trying to estimate, and so the values that you plug in are for x and w. Let me, we'll do this in the example, and you'll get a chance to see it in action, and it will make a little more sense once we have something more than letters. Okay. Questions? Yeah?
You type 2 x to in front of 3 and 4.
To what?
Like here, z line x z 3. I
Mm-hmm.
guess it would be, and then the next is it w z 4.
Oh, yes, thank you. I need that one. Is that right? Okay, thank you. Yeah, copy paste error. But yeah, you have to figure out which is the variable you want the slope for. And that is held constant at 1, always. Elsewhere, you plug in the values for the moderators, the other variables that is not the slope for. But the same logic that we use to build these simple main effects, we're now going to use to build simple two-way interactions, where simple is not meant like it's easy, but that it's conditional. So the model tells us how x by z would be for any value of w. So how do I figure this out? Same rule. The only terms that go down here are those that contain x by z. So I don't need the intercept, I don't need any main effects. That one doesn't have x by z, this one does. So I've got a beta 5 plus, what else? Beta 7 times w, exactly. So the only time in which beta 5 gives you the x by z interaction is when w is 0 and this part drops. We can do the same thing down here for x by w. That one is beta 6 plus beta 7 times what? Which one is the moderator? Yeah, z is the one that's left out. And then this one would be beta z. Oh, no, I got it wrong. That one's 4. Thank you. Yep. Times x. There you go. Got it. And that's how we do it. Cool, huh? You think it's cool? You're just smiling because I said cool. Yeah, I think it's cool.
And the package from R is G models
G models? Okay.
I guess the function that I used from that one is estimable.
Estimable, because estimate was already taken. Nice. So let's see. Yeah. So let's see this in action. Welcome back, it tells me. Let's pick up to where I left off. Where I left off was page 5 of example 2B. So we're returning back to the same data sets and modeling set of models that we're looking at from chapter 2. Just to remind you, these are 550 older adults. We're predicting cognition from, excuse me, coughing fit. Chronological age, which has been centered at 85 because that was near the mean. Grip strength, which is a measure of physical, functioning, I guess, in older adults is the best way to put it, which is centered at 9 pounds per square inch. We have a variable for gender, which is coded men are 0 and women are 1. And we also have 2 dummy codes to differentiate among our 3 dementia groups, where none is the reference. The first one differentiates none versus future, and the second differentiates none versus current. So I am creating fake people. Remember this, those of you who were here? I am adding cases to the data set that have values of the covariates for which I want to generate predictions and put them in a figure. I'm going to add these fake cases to the data set, run the model on them. Because they don't have any outcomes, they're not going to ruin anything, but they will get predictions when I ask for predicted outcomes from the fixed effects, the same as the real people, except that now I can just plug these into any graphing program, and these will form the points for my figure. So in anticipation of the 3-way interaction that we're going to look at here between grip, age, and gender, I am creating people that have plus or minus roughly 1 standard deviation on grip strength. So plus or minus 3, who are either age 80, 85, or 90 in age, and then who are men versus women. And the other 2 columns are holding dementia group constant at none, because we're going to look at interactions involving them in the next example. So we're leaving that to the side for right now. So here's my model. The new terms relative to what we looked at last time are underlined. I've added interactions of dementia group by gender. We're going to focus on those next time, but they're here because that's what we had in the chapter example for continuity. And I'm going to have us look at the age by grip by gender interaction, which implies that we have already added the 2-way interactions that are nested within them, age by gender and grip by gender. Okay, so take a look at that, see if you have any questions on the model. So here are all of the main effects on the first line here, all the 2-way interactions on the second line, and the 3-way interactions on the last line. What is this? It looks like a space is missing. There we go. There. Two more 2-way interactions and then the 3-way. Now for completeness, I've listed all of these out, but that's a lot of typing. Do you want to see a shortcut? If you replace the stars with bars like this in SAS, do you know what it does? It gives you all possible main effects and lower order interactions. So that way you won't forget any. It's very handy. I think Stata has something with I want to say 2 pound signs that does something similar. SPSS does not, to the best of my knowledge, but that's just a little trick that I teach people once I trust them enough to be able to use it wisely. Before then, I want them to remember that every time you add this three-way interaction, the model is only correct if you have everything that's underneath it, which is these 3 two-way interactions and the 3 main effects. So just as we just did in the PowerPoint, figure out, first step here, let's get some simple main effects of age. So how does the model tell us what the effect of age is going to be at varying levels of grip strength and for both genders? Well, I pull out every term that has something to do with age. So I need beta 1, I need beta 6, age by grip, beta 9, age by gender, and I need the three-way interaction. If I move age to the front, if I factor out age, then the term in brackets here, that's what goes in my estimate statement. So the statements that go with this then for various values of the moderating variables are below. So I'm asking for the simple effect of age, so that's age and then a 1. What that means is that at a minimum, I need 1 beta 1 to create the simple effect of age, because that's what it would be for the reference group for gender and grip strength. Then I pick up age by grip, and because age has already been given a value of 1, the two-way interaction of age by grip takes a value according to which grip I want. And this is for somebody with -1 standard deviation, which happens to be 3, so I put a -3 here. So relative to 9, this would be a grip strength of 6 pounds per square inch. Likewise, the two-way interaction of age by gender, we've already given age the 1, so the value that goes into age by gender is the value for gender. So this is for a man. And then last but not least, -3 times 0 is 0. Or more specifically, 1 is what we code age, -3 is grip, and 0 is gender, which knocks the whole thing to 0. So this line right here, that's my reference. That's the effective age that would be given by the model just as beta 1. It's the only line in which all of the other terms are zeroed out. But you can see the patterns, hopefully. The first 3 lines are for a man, so gender goes to 0. Women are a 1 code. And then I have plus or minus 1, so -1, 0, 1 standard deviation of grip. And then the multiplication gives me the final coefficients out on the end.
Does it make sense to use any number besides 1 for age?
Nope. Because what you're asking for is how many beta 1s you need.
Yeah.
And you only need 1. Okay, other questions? Okay, let's do it for grip strength. Same strategy. Go back to the main equation, pull out all the terms that have grip in them, factor out grip, and the term that's left begins with the simple main effect of grip, the two-way interactions of grip by age and grip by gender, and then the three-way interaction. So now it's grip 1 that starts everything off, because at a minimum, the simple effect of grip is given by beta 2. Then we fill in the value for age, for which we want the grip strength slope, according to the two-way interaction of age by grip. We fill in the value for gender, for which we want the grip strength slope, and then we do the multiplication to figure out the three-way interaction coefficients. Same deal at the bottom. Now this is the simple effect of gender as a function of age, as a function of grip, and as a function of age by grip. Where instead of plus or minus standard deviation, I picked plus or minus 5 years because I thought, well, 80, 85, 90, that's a nice round number I can put on my plots. It's an arbitrary distinction. Good so far? Okay, now the new part. Simple or conditional two-way interactions. So age by grip is the first one. I've asked for the age by grip interaction for men and for women. Which one of these is already given to me as a model coefficient? The men or the women? The men, yeah. So the model already tells me what the age by grip interaction is for men. The three-way interaction tells me how it differs for women. To get to what it is for women, I add the two together. The next one is age by gender, and here I'm plugging in somewhat arbitrary values of grip strength. So what does the age by gender interaction look like for somebody who's relatively weak, for somebody who's average, which is what the model coefficient would give us, and for somebody who's relatively strong? Likewise, grip by gender for somebody who's relatively young, average, or older. Okay, with me? So this is the math part. This is the part that's easy for this group, right? You're all good at math, except me. I'm better at words. But the words are the important part to communicate what the heck this means to anyone else who would care. So I want to point out here, SAS told me that it did not use 18 observations. Those are my fake people. So that's good news. It shouldn't use fake people in estimating the model. The only reason I put them in is because of this command, back, right here. Do you remember what that does? Those of you who were here last time? This makes me a copy of my data set with new columns for predicted outcomes from the model fixed effects for every single case in my data set, including my fake people. So it's an easy way to create predicted outcomes for making pictures. Okay, so here we go. Let's just start with the model fixed effects. So intercept. Expected outcome for what kind of person? Age 85, grip 9, a dude without dementia. Okay. We will focus on the dementia effects and their interaction with gender later. What I want to focus on are the age, grip, and gender main effects, two-way interactions, and three-way interactions. So let's start with age as one of them. Who'd like to put 0.49, negative 0.49 in a sentence? Let's call it minus 0.5. I'm going to call on Ismail, since you were late. You haven't had a turn yet.
Which one?
You haven't had a turn yet. I made everybody before you got here
Okay.
answer questions. So put this number in a sentence for me, please. Make it even bigger.
What's the dependent variable?
Dependent variable is cognition.
Okay. Cognition will decrease by 0.49 units for every 1 unit change in age when the linear effects of the main effects and the linear effects of the grip, sex, and the other variables are held constant.
Not just held constant.
also when their interactions are.
So so you're on the right track. So for every 1 year older,
Yes.
cognition declines by a half a point.
Yes.
And that is, and you want to say holding constant everything else in the model, right?
Yes.
Holding constant dementia group and gender and grip, but not, it's holding constant dementia group because age doesn't interact with dementia group, but it's not just holding constant for grip and gender because it interacts.
Yes.
So it's holding constant grip at 9 and holding constant gender at males. So this is the age slope specifically in average strength men. That's what that means. So that's my reference point for the sentences that follow. So age is bad for you if you're a man of average strength. So everything that follows then, because this is negative, going to be more bad or less bad, right? So if I go to, let's go age by grip as the next one. This is the age slope for somebody with a grip of 9 in men. What happens to that age slope according to the age by grip interaction? This one's open to anyone. Now we've all had a turn.
It's less bad. Or
Less
every-
bad, yes. Less negative, right? Which in this case means less bad. A less of a decrease. Now put the number in the sentence. That's the tricky part. For every. That's always how it starts. For every 1 unit more pounds per square inch of grip strength, for every additional pound, what happens to the age slope?
The age slope becomes less negative by 0.23.
There it is, the age
Units.
slope. Yep. The age slope is the unit of the sentence now. We're not talking about cognition. Age affects cognition. Grip by age affects age. It's like a trickle-down kind of system. So yes, for every 1 pound more grip strength, that slope becomes less negative by 0.23. And then going back to what you said to begin with, age is less bad for you if you're strong. Girl. But now both of these are true in what kind of person? No. The third variable. Men. Okay, so age is bad for you, but age is less bad if you're stronger. But that pattern is for men. Now we pick up the third one. And I know this isn't significant, but just play along as if it were, because I want you to know what to do with the numbers. So the 3-way interaction moderates the 2-way. So I would say the 2-way interaction of age by grip is less positive in women by 0.15. Now, what the hell does that mean, right? This is where you got to wordsmith your way out of this. Well, so the extent to which being stronger diminishes the effect of age is reduced in women. I'll say that again. The extent to which being stronger diminishes the effect of age is reduced in women. And the fact that I'm doing this with a cold, do I get some credit for this? Yeah, I know, right? Thank you. Thank you. But this just goes to show once you learn this, you can't unlearn it. Like it's algorithmic.
So how would our words change if our simple main effect was grip 9 instead of age 85?
What a great question. Let's do that. Let's start here.
We'll still be talking about that.
And then go here. All right. So grip 9, for every pound stronger you are, cognition is higher by 0.74 in 85-year-old men. Now let's come down to the two-way. What happens to the effect of grip in older people? Increases. The slope for grip is more positive by 0.23 per year of age. So being strong is more better for you if you're older. I said I had words. I didn't say they were sophisticated words, but more better. So it's good to be strong. It's even more important to be strong if you're old, but these are both in men. Now let's pick up the third. That tendency for it to be more important to be strong if you're old is reduced in women. Let's go another way. Let's go grip to grip by gender to the three-way. Let's go that way. Okay. Being strong is good for you if you're a dude who's 85. Now down to the two-way. What does that two-way interaction with gender do to the main effect of grip? Less positive in women, right? So the benefit of strength is reduced in women. Not there yet. Not there yet. The benefit of strength is reduced in women. And now we go down here. Even more so in older people. Yep. Because this three-way interaction takes this two-way and makes it more negative as a function of age. So yes, the benefit of strength is reduced in women, comma, even more so in older people. That's a three-way interaction sentence.
Would we have to say women that are aged 85 in the two-way?
Yep, this two-way is for 85-year-olds.
85.
Yep, these are both for 85-year-olds. So then this tendency for the strength effect to be reduced in women is enhanced by age. How about, let's do age by gender, by strength. Oh, that's a tough one. Okay, so age is bad for you. Start there. What does the two-way interaction do to it? Less negative in The effective age is less negative in women, so less bad for you. However, yeah, this is a tricky one. Because I'd be inclined to say less positive, right? But it's very quickly heading negative. So I would accept either less positive or more negative as strength increases on that one. So which way you go through these, entirely up to you. It's sometimes easier, I think, to think about this two-way interaction and how it varies by gender. I think that's probably the most natural for me, but it's up to you. Here are the results of all of my estimate statements. So if you wanted to know if a predictor was significant for a certain type of person, whether or not they were the reference group, that's what these things can tell you. They can also confirm your intuitions about what happens as things increase or decrease to make sure you've got the patterns right. And here are the two-way interactions that are conditional on the third variable. So age by grip, that interaction is reduced in women. Age by sex, that interaction is, I would say, less positive into negative as strength increases. That's the one that we just saw. Grip by sex is less positive into negative as age increases. And it will always be helpful to make a picture. So, did you guys go to poster sessions at the conference? Did you see people whose posters had tables that looked like this? And did you want to shoot them? Because this is lazy. This is just plain lazy. This is not how you present information for someone to digest it in 30 seconds. This is, do not put this in a poster or a talk. This is what goes on your poster. Pictures. So these pictures, what I have is the age by group interaction plotted separately for men and women. So if we look at that was the first one that we did. Age is bad for you. Age is less bad for you if you're stronger in men. And that tendency for age to be less bad for you if you're stronger is reduced in women. The lines are not as far apart. And that's your bullet. It takes a lot of work to get from this to that, but this is the story.
This is grip 12 a little bit weird here.
Well, so this brings up an interesting question. This is like the effective grip controlling for gender. To what extent there are women with a grip strength of 12, like I don't know, right? I'm assuming that these distributions for grip from plus or minus 1 standard deviation are gender invariant, but they're probably not. That's one thing you'd want to make sure is that there are, like that these points are plausible given the distribution of your variables and the combinations thereof. And if you want my words, they're in the end of chapter 2. So all the words that came out of my face today are in there somewhere. So, how are we doing? Questions on any of this logic? Or why it matters? Where people tend to go wrong is in looking at the output. Let me go back down here. that's given by default, right? And you'll see people, let's say that this interaction was significant and they're going to write this up. You'll see people talk about like the main effect of age and the main effect of grip as if it's significant or not significant. But this age effect is only one of an infinite number of possible age effects that this model gives you. There's not just one age effect. There are many, many, many. And so you have to be very careful to conditionalize this, because when you don't have your interactions in the model, this is the age effect for everybody. As you start adding things, it becomes more and more specific and less generalizable. There was an example table published in APA, like how to make tables for your picture book. And they had an example regression table where they had the main effects in a stepwise regression, and then they did not repeat them. They had just the interaction terms added on the next layer. Yeah, that's wrong. That's way, way, way wrong. The main effects that come from a main effects only model are not the same main effects that come from the interactions model. They're marginal versus conditional. If you've mean-centered all of your predictors, they'll be close, but they're not going to be the same, and certainly the standard errors aren't going to be the same. So, when you have this interaction in the model, everything is conditional, even if it's not significant. So like this being non-significant, even though it's non-significant, it still means that this effect of grip strength up here is for men. The fact that this is non-significant means that it's not that different for women, but this is still for men because this is in the model. And if you're going to have the three-way interaction, you have to have all the two ways that go with it, otherwise it's not really the three-way interaction.
And did you already draw out like estimate statements if we wanted to get, say we have all the interactions, what we want to get, say, the average effective age across all grip strengths and sexes?
You would have to plug in, let me find, here's some age effects. So to do that, you would do age 1, and then you would have to plug in the sample mean values for all the other predictors into these.
The means.
Mm-hmm. I mean, that would be how you marginalize across your sample. Now, that brings up an interesting point. You could easily find the mean for grip strength. You could easily find the mean, but what would the mean for gender be? Right? Like, in this sample, I think it's maybe 60% women or something, so you'd put in like a 0.6. But then it's the age slope for someone with a gender of 0.6, which, like, it'll give it to you, but what? So that's where it starts to get a little bit weird.
Yeah. I guess then you just have to draw the conclusion based, or describe the outcome on the basis of like the population that you're describing instead of like an individual person.
Well, that, yeah, I mean, but it also brings up, like, in some samples, like so you'll see this in the next example, gender, when it marginalizes over gender, it weights the two genders 50-50 in computing the marginal means. But if that's not what it is in your sample, then that's not, like what are you trying to generalize to, is the question. There is a way to tell it to use the weights that are present in your sample, if you know in reality that one group is much more prevalent than the other. And then that would maybe be more generalizable, but it's also more like dependent on you having sampled correctly and believing in your strategy. But yeah, I mean, what does the average age effect look like? Well, it's hard for me to think about an average gender. But there's nothing wrong with mathematically thinking it that way. You can do regions of significance for three-way interactions like this. The process is the same as what I showed you before. It's just that the two-way interactions would take the place of the main effects in that case. So, other questions? I think we can be done for today. If not, I don't have the strength to go through another example. Does that sound good? Yeah. Other questions? Thoughts? And you realize this has nothing to do with longitudinal, right? This is all stuff that I wish that you learned in your initial regression class, but I can't be sure that you did, and so I have to give it to you now. So, These techniques are useful whether you're dealing with a structural equation model and these are latent variables and you have moderation, or you're dealing with logistic regression and these are all in logits. This idea of decomposing interactions via main effects holds no matter what kind of model you have. So, very useful tool. All right, well then, it can be done.
How does SAS know about the records that you append to the original data? They are like fake people.
Mm-hmm.
I noticed that you told the ID to negative 99. Is it the default option? Does SAS will identify those people as fake people?
So I picked negative 99 as my ID because then when you sort the data set, they're first. And I can just go in and grab those values very easily when I open up the data.
Uh-huh.
But the reason that SAS knows they're fake is that they don't have an outcome.
Oh.
They only have predictors. So they
So
can't...
that's like list-wise division, like they divide them for the
Yep,
analysis.
they do. What happens, so this is the very first table here. It said that it read in 568 cases, it used 550 and it didn't use 18. It didn't use my fake people to estimate the model.
Oh, okay. I saw it's like SAS knows like that ID.
Nope. No, it's just, this is, I printed the data set that I asked for, and there's a pred column. And this is for everybody in my data set. I just truncated it to just my fake people. And it's the prediction based on the model fixed effects. And that's what I use to make the pictures. So I could have written out the model like in Excel and generated the predictions myself, but then I'd have to enter all of the coefficients, and anytime I change the model, I have to change all of that. Whereas if I change the model here, it automatically updates because my fake people have the values that I want to plot no matter what the model is. So if you think about ahead of time what you want to show, you can introduce cases into your data set just for the purpose of doing that, and they don't mess anything up because they don't have an outcome. Just as an aside, make sure it's the fixed effects that you're predicting. Where is it? Find this right here. So all programs have an option to predict based on the fixed effects or the random effects. We want fixed effects in the plots. Random effects are person-specific predictions. You could use those for things, but it's pretty rare that you'd want to. Right. Other questions? All right, then I'm signing off for now. Office hours, if anybody wants to talk to me, I'll try not to cough all over you. And hope to see you next Tuesday. We'll do some more interactions with categorical variables. Yeah. And I'll tell you why I hate ANOVA output.